Section 9.5, linear system of differential equations. This is like when you have multiple differential equations at the same time and you were asked to find the unknown functions. This is also the same as section 7.1 and 7.3 in Larson's book, 9.5 in Lay's textbook or Nagel's textbook. So a general homogeneous first order system with constant coefficients in vector notation looks like this, where A is n by n matrix, x is the solution, x prime is the derivative of your unknown functions, and they are functions of independent variable t. So this is a typical linear homogeneous first order differential equation with constant coefficient looks like x1 prime is equal to constant x1 plus some constant x2 all the way some constant xn. x2 prime and also is a linear combination of x1 through x2n all the way to xn prime. So these are the so the unknowns are x1, x2 all the way to xn, and these a11 all the way to an are constants. If you recall, when we solved the second order homogeneous linear equation with constant coefficients, the fundamental solutions had this format: e to the power of rx, e to the power of r2x. In other words, the solutions were exponential functions, which the linear combination of those exponential functions constituted the general solution. The same thing was true when we had, let's say, first order dy dx equals y. When we solved it, once again, the fundamental solution looks like an exponential function. So it is reasonable to anticipate that the solution of what? System of differential equation would look like something with exponential function. And turns out that's true, meaning the solution of this system of linear differential equation homogeneous with constant coefficient happens to be equal to v times e to the power of lambda t, where lambda, of course, is the eigenvalue of the matrix A, and v is the eigenvector of matrix A, and of course, it cannot be what? Zero vector, correct? It's really easy to check. All you have to do is take the derivative of this guy, and lo and behold, because e to the lambda t is not equal to 0, divide both sides of this equation by e to the lambda t, and you get the precise definition of what eigenvalues and eigenvectors. So AV equals lambda v. This implies v is not equal to 0. So what? V is an eigenvector associated with the eigenvalue. So here's a theorem. The theorem says if lambda is the eigenvalue of what? Of the constant coefficient matrix A of the first order what? System. So remember, this is how we show the system of linear homogeneous differential equations, or sometimes you can write it at x prime of t equals a sub n11 times x of t. So these are equivalent statements. Incidentally, the reason they call these homogeneous because there are no other additional functions added to this. In other words, a non-homogeneous first order differential equation would look like ax plus some column vector or some vector of functions of t, for instance. Notice in this case we have x prime e to the tx1 t squared x2 sine of t, and then t1 x1 plus 3x2 minus cosine of t. So The homogeneous kind does not have these additional what functions on the right side. Incidentally, this is like variable coefficients, but the ones we'll be dealing with, all the coefficients will be constant. So back to the theorem. So if lambda is eigenvalue and v is the what corresponding eigenvector, so the solution should look like what? V times e to the power of lambda I, which is a non-trivial solution, correct? So you can also verify that, and then it is true. So let's get right to it. So here's the final, the general solution of the system. Notice this is a system of differential equation. The reason we call that system, because we have two differential equations simultaneously at the same time. When the word is solve or find a general solution, the objective is find what? X of t and y of t. Unfortunately, we can't solve these equations one at a time because the equations are coupled. What does that mean? X prime has y in it, y prime has x in it, so you can't solve these simultaneously. What you could do is put this in matrix notation form. So here's a matrix A, which is 2 by 2, and this is your what? Unknown function vectors, and these are what? The derivatives. So this is how the same what equations look like in vector notation. So what you do, just like before, we find the eigenvalues and corresponding eigenvectors. So it turns out eigenvalues are 3 and 2. If lambda 1 is equal to 3, the corresponding eigenvalue is v1, which is 1, 1. If lambda 2 is equal to 2, the corresponding eigenvector is what? v2, which is 2, 1. So therefore, the vectors, these are vectors, remember, just fundamental solutions are vectors, is what? 1, 1 times e to the what? 3t, and 1, 2, 1 e to the 2t, right? Remember the solution was v times e to the lambda t. So here is what? v1 e to the lambda 1t, and this guy is v2 e to the power of lambda 2t. So these are our fundamental solutions, correct? Fundamental set of what? Solutions. So any linear combination of this will give you the general solution. So the general solution is x of t, which in our case is x and y, which is c1 times what? v1 e to the lambda 1t plus c2 times v2 e to the lambda 2. So if you kind of expand this, that means multiply these functions by these vectors and kind of add up the vectors. At the end of the day, you will end up with something like this. So if you add these two vectors, you get this. So now you got a vector on the left side, you got a vector on the right side. Two vectors are said to be equal if the corresponding components match. So what does that mean? That means x of t has to be c1 e to the 3t plus 2c2 e to the 2t, and y of t is c1 e to the 3t plus c2 e to the 2t. This is our final answer. So this is how x should look like, and this is how y should look like. Remember, the objective of the problem was you had a system of differential equation, linear homogeneous. You were supposed to find the unknown functions. So in this case, your unknown functions are two, one for x, the other one for y. Here's the other method to solve a system of linear equation, which involves a what? 2 by 2 matrix. Okay, so in this case, the coefficients are A, B, C, D. What you could do is what? Solve equation number 1 for y, take its derivative, okay, then substitute 4 into 2, and lo and behold, once you go through all these manipulations, then what's going to happen is we're going to end up with something like this, which is second derivative of x with respect to t minus a times first derivative minus d times first derivative minus cbx plus adx. But if you kind of group the like terms and kind of clean that up, you would get second derivative of x with respect to t minus a plus t dx dt plus ad minus bc times x equals 0. Call a plus d beta, call ad minus what? bc gamma. So change your system of equation into a single second order linear homogeneous differential equation with constant coefficients, and that would be this guy. However, if you carefully look at the matrix, which was A, B, C, D, A plus D is what? Is the trace of matrix A, and that's beta. And gamma, AD minus BC, is the determinant of matrix A. So if you go back to the same problem, you can see beta, which is the trace of matrix A, is 5. Gamma is the determinant, which is 6. So I can write this system of equation as a single second order homogeneous differential equation with constant coefficients. So as a result, I get what? X double prime of t minus 5x prime of t plus 6x equals 0. This is the auxiliary polynomial, so these are the roots of auxiliary polynomial. So the fundamental solutions are e to the 3t, e to the 2t. So linear combination of these guys constitutes what? The unknown function x of t. Now all you have to do is take the derivative of x of t and substitute that in equation number 1 and get your y. And that's exactly what I did. I have taken the derivative of my x of t solution. Then I substituted the 3 into what? I guess in this case, where'd it go? 1, right. And then I solve for y. And believe it or not, you get exactly the same answer. All right. When you solve system of differential equation, turns out these are the kind of, if this system is describing the behavior of a mechanical system or electronic system, then there is this point called equilibrium point, which is what? Which means there is no rate of change in x or y variables. In other words, dx dt equals dy dt equals 0. So in our previous example, if you set what? These guys equal to 0, solve for x and y, turns out the equilibrium point would be 0, 0. So in our case, we say the system at 0, 0 is unstable. Why? Because as t approaches infinity, notice these guys approach to what? Infinity as well. So in other words, beta is positive, gamma is positive. If beta and gamma is positive, 0, 0 is an unstable point. So based on the signs of the gamma and beta, and also the signs of eigenvalues, you can also determine, your equilibrium point is either saddle, stable, unstable, sink, or source. So if gamma is negative, your equilibrium point is saddle. So that means what? The solution curves, some of them they get close to 0, 0, but some of them go away from 0, 0. If gamma is positive, beta is negative, then it's stable. In other words, after the system goes through motion, at the end of the day, at t approaches infinity, all the solution curves converge to 0, 0. So that's a stable node. That's N-E-N-O-D-E, node. If gamma is what? Positive, beta is positive, 0, 0 is unstable. Notice all the solution curves are divergent away from the what? From 0, 0, so that's kind of like a source. If gamma is positive, beta is 0, then your equilibrium point is center. So that means the solution curve centers around the what? 0, 0. If beta square minus 4 gamma is less than 0, then either you have a sink or source, and then you would have a stable spiral or stable what? Spiral, which is either unstable or stable. So, so if it is what? Um, like on a spiral stable, so that would be sink. Unstable spiral, that would be source. So remember, source, the solution curves go away from the equilibrium point, and for sink, they approach to. But in these cases, they approach what? In a spiral fashion. So now, sometimes you may have system of differential equation, which is IVP, initial value problem. So in this case, the word solve means find a particular solution. Why? Because they have given you initial conditions. Do you see it? The question is solve the system of differential equation when x1, 0 is 1, x2, 0 is 0. So remember, we found the solution. Let's say this is the solution for this system. So all you have to do is what? Impose the initial conditions. So these are the initial conditions. And you get a system of linear equation in terms of C1, C2. Solve C1, C2, and you get your what? Particular solution, which happens to be unique. So this is it, right? Um, Sometimes when you solve a system of linear differential equation homogeneous with constant coefficient, like let's say in this case 3 by 3, sometimes you get multiplicity for what? Eigenvalues, correct? In this case, lambda 1 is equal to -1 with multiplicity 1. Lambda 2 is equal to 2 with multiplicity 2. If lambda 1 is equal to -1, its corresponding eigenvector is what? 1, 1, 1. If lambda 2, which is the same as lambda 3, so this is also the same as lambda 3, is 2, then you get two linearly independent what? Eigenvectors. And so this guy is going to be minus 3 halves. So this is like minus 3 halves, 0, 1. So these are your fundamental set of solutions, which they happen to be vectors. A linear combination of these guys constitute the general solution. But notice when it comes to solving system of linear differential equations, notice there is no factor of t, even though we have a repeated root. Remember in solving what? Nth order differential equation, linear homogeneous, if we had what? Auxiliary polynomial got repeated, remember we would have a factor of t in one of the fundamental solutions, not here. So be careful, even though lambda 2 and 3 is equal to 2, which is multiplicity 2, but no factor of t. So don't put a C3t e to the 2t. It doesn't work for system of linear equations. So if you multiply these what? Functions of t by these vectors, you get this. And now you have a vector on the right side. So in this case, x of t is x1, x2, x3. That's what x of t is. Add these vectors up. And now you got a vector on the left, vector on the right. So x1 is this expression, x2 is that expression, x3 is that expression. There it is. So you got three answers. But the point of bringing this example was, even though there is a multiplicity of eigenvalues, there is no factor of t attached to one of these fundamental solutions, which you got by replacing the lambdas with 2. Be careful. Sometimes it's impossible to solve the system of linear homogeneous differential equation with constant coefficients uh, by what? Eigenvalues and eigenvectors. Suppose you were asked to solve, so the corresponding matrix of coefficients happens to be 1, 1, 0, 1. When you do the computation to find the lambda, lambda is equal to 1 with multiplicity 2, so you get the repeated roots, correct? But when you solve, you get infinite many solution as you're supposed to, always, rain or shine. R here is a real number, but the only if you factor out the R, the only linearly independent eigenvector for lambda is equal to 1, which was repeated, is just 1, 0. So the eigenvectors associated with lambda falls, I should say, falls short of the number of times lambda occurs as a root of characteristic polynomial. So therefore A is defective matrix, so we have not enough linearly independent to match its size. Therefore, I cannot solve this system using eigenvalues and eigenvectors because the corresponding matrix of coefficients happens to be defective. Do you see it? Now, sometimes when you find the eigenvalues of the corresponding matrix of coefficients, like in this case, you get complex roots. Notice if you set lambda squared plus 4 equals 0, you get lambda is equal to plus or minus 2i. Remember, I was the complex number, -1. So in these cases, we have a fact that says if you have a matrix n by n and lambda is a complex eigenvalue of A with non-zero eigen vector V, then the conjugate of this lambda is an eigenvalue of A, and the conjugate of this eigenvector is also an eigenvector of the matrix A. So what does that mean? That means if I have, let's say for example, if I have lambda 1 is equal to, let's say, 1 minus 3i, you know lambda 2 is going to be 1 plus 3i. So we call 1 plus 3i the conjugate of lambda 1. And let's say the corresponding vector for lambda 1 came up to, let's say, I'm just making this up, 1 minus I, 5, let's say. So you know for sure what eigenvector number 2 is conjugate of this. So that will be 1 plus I, 5. Don't go by changing the sign of 5 to -5. That's not conjugate. Why? Real numbers don't have conjugate. Anyways, so when you form the augmented matrix and replace the lambdas here with what? Let's say we try positive 2i only, we get something like this. So what happens is this time v2 will be, so if you read the first row, -2i v1 plus 2v2, so this indicates we have infinite many solutions. So from row 1, -2i v1 plus 2v2, so v2 is equal to what? Is equal to, or I should say, v1 is equal to what? Oh, -2 v2 over negative 2i, correct? So anyways, so what happens is we will end up with what? E to the power of 2it times what? Negative I1. So in other words, what's going to happen is here, you're going to get something like, let's say, S what? Uh, what? Let's see now. Negative, let's say SIS, where S is a complex number, but the only linearly independent eigenvectors for this particular case, if you factor out the S, you get negative I1. So S is a complex number. So this is the only linearly independent what? Vector for when lambda is equal to 2i. Notice the eigenvector also is a complex vector. Do you see it? So the solution, the complex solution of the form, it has the form e to the power of lambda t times v, remember? But Euler's formula says you can rewrite this portion as what? Cosine of 2t plus I sine of 2t. Multiply this complex function by this vector, and you get this, okay? Then you split this and kind of separate the reals from the imaginaries. You get something like this, sine of 2t cosine of 2t plus I minus cosine of 2t sine of 2t. So these guys, these two guys, happens to be two linearly independent real, so here's the catchword, real solutions to the system of differential equation. Remember, your final answer should have no I in it, correct? So any linear combination of this will constitute the final answer. So if you take C1 times this times e to the what? Um, let's see now. Right. Where are we? 0t, okay. And C2 times what? Minus cosine 2t sine 2t e to the 0t. And this is what you get. So equating what? So this guy is the same as what? X1 and x2 is equal to this, what is it? 2 by 1 matrix. So we got a matrix, vector on the left side and vector on the right side. And lo and behold, you get what? X1 is equal to this expression, and x2 is that expression. Do you see it? Incidentally, the reason I got 0, because remember lambda 1 was 0 plus 2i. Remember, a is 0, b is what? 2. That's why I'm getting e to the 0. So whenever lambdas are complex, just like, system, nth order differential equations, when we did way back in previous chapters, you can bet your money that what? Your solution is going to have sine and cosine in it. So finally, the question is, how do you determine the linear independency of what? Bunch of vector value functions. Well, turns out we have a special Wronskian. So this is not your good old Wronskian. Remember the good old Wronskian for function of real values, where you would list the functions in row 1 and then row 2 with the first derivative, row 3 will be second derivative, and so on and so forth. But for vector value functions, we have to have a special Wronskian, which means there is absolutely no derivative involved. So all you have to do is what? List the what? First vector value function in column 1, second vector value function in column 2, all the way, so you get an n by n determinant, and now evaluate. Okay? So If this Wronskian is not equal to 0 for any value of t in some open interval, then we say these vector value functions are independent, right? Otherwise, the test fails, so you gotta do the definition. The definition would be C1x1, C2x2, all the way to Cnxn is equal to 0. And see if all the c's are 0, so you can say these vector value functions are linearly independent. If one or more of these c's is not 0, then they're linearly dependent. So here's a couple of examples for you. Suppose x1 looks like this guy, x2 looks like this, and x3 looks like this. Question, determine if these guys are linearly independent or dependent. Notice there's absolutely no derivative. Remember, this is special Wronskian. So what I did, I listed what? X1 in column 1, X2 in column 2, and X3 in column 3, and I came up with -3, which is not equal to 0. So the conclusion is they are linearly independent for any t from -infinity to infinity. Regardless of what t is, this is always -3. However, my second example, here is your x1, here is your x2, here is your x3. These guys are linearly dependent. Why? Because if you look at these vectors carefully, 3 times x1 minus what? Twice of this is the same as x3. In other words, what we're saying is x3 is equal to, what did I say? 3x1 minus what? 2x2. So obviously the C1, C2, C3, C1, C2, C3 are not equal, all not equal to 0. Therefore, these three vector value functions are linearly dependent. So don't forget, we have special Wronskian, which is not the same as good old Wronskian for what? Functions of real values. Thank you.